Hello, everyone. Welcome to our webinar today, Planning Your CHP Arrangement. We will get kicked off here in just a moment. Well, just wait a little bit while folks start filing in. Okay, so out of respect for all of our very busy schedules on a beautiful day, if you're where I am in Michigan, let's get going. So welcome to our Commonwealth webinar session, Planning Your CHP Arrangements, General Considerations of Combined Heating and Power Plants. My name is Del Belcher. I'm the Marketing Manager for Commonwealth Associates. In today's webinar, it is designed for professionals in power generation engineering at any level, especially those involved with CHP layouts and design. Next slide, please. A little bit about Commonwealth Associates. So Commonwealth, we provide expert engineering and consulting services that enable a more reliable, resilient power system. We like to collaborate with diverse energy industry stakeholders, tackle intricate energy engineering challenges, and our areas of expertise encompass renewable energy studies, consulting, as well as power delivery, power generation, and what we're going to be talking about today. You can find out more about us at commonwealthassociates.com. Quick note about today's webinar. It is advertised as being available for a PDH credit, and that is true. So today's webinar is worth 1 professional development credit. The process for claiming credits varies by state. There's different requirements, but to accommodate for this, you're going to receive 2 items to help you make sure you get that credit. One, you're going to get a certificate from GoToWebinar confirming your completion of the webinar. That'll come to your email from the GoToWebinar team. An email from the webinar team, that's us, on Commonwealth, reiterating and confirming the validity of the certificate as proof of the PDH earned. So you'll get the certificate, then you'll get another email saying, yeah, that certificate, that's what people are using, that's what you can use and to count. So submit those 2 things together, and that will be, in most cases, enough proof for you to claim your credit. Also, we're going to be having a Q&A session immediately after the main portion of the presentation. So if you have any questions or you'd like to submit a question, comment, or are interested in getting a follow-up, you can do that. And we'll talk about how to do that here right now. Next slide, please. Some tips for engaging, and this will also be where you can submit your question. You'll see your GoToWebinar control panel. It has many buttons, lots of things going on there. There's audio. Press that for your audio preferences. If you'd like to ask a question, you go to that questions tab, click that. You can submit your question, and we'll make sure to get that for the Q&A time. There's also a chat that you can hit and connect with people in the chat. It's open and public to everyone, or you can message me directly if you're having some technical issues. And also there's a handouts one. We don't have any handouts for today, so you don't need to worry too much about that. Next slide, please. Lastly, we have an upcoming webinar, October 23rd. It's on 3D modeling. 3D modeling is an important aspect of our work with plants, and redesigns, and studies and things. And Kent's actually going to be, this is actually a picture from your presentation. So he'll talk a little bit about it. And if you'd like to know more about that specifically, that modeling, we'll have a session coming up in October all about it. So next slide. Let me introduce, before you get started, Ken, I got to do a little introduction. So as you all know, CHP plants can generate both electricity and heat, typically from a single fuel source. This achieves higher efficiency, reduces emissions compared to traditional methods, and can save money. In this webinar, we're going to talk about all the considerations you need to, all of the considerations, I don't know about all, but most of the considerations you'll need to make when designing your CHP plant. And to tell us about that is our presenter, Kent Melville. Kent is a seasoned senior mechanical engineer technician at Commonwealth. He boasts 35 years of hands-on experience in mechanical drafting and piping design. His experience and expertise span power engineering and automotive realms. and Kent's forte lies in a lot of things. And I'm going to let him tell you more about them throughout his presentation. So I'd like to introduce everyone to Kent. Hello, Kent.
Hello.
Welcome. And it's up to you now. So thanks for being our presenter today, and we look forward to what you have to say.
Okay, I'm going to turn my camera off.
Yeah, me too.
So first I want to say thanks to the marketing team that helped pull the presentation together, as well as some of the engineers that I work with and the top-notch designers that are part of our team here at Commonwealth for some of their input in pulling all of this together. My agenda is going to start with a basic review covering the CHP options that were presented in a webinar Commonwealth gave back in June of last year. That presentation was titled Small Scale CHP for Universities, Industrial, and Commercial Facilities. Then I'll touch briefly on the remaining bullet points with some considerations related to layout and space requirements. The considerations covered will help to provide a well-planned general arrangement that is beneficial for construction, efficient operation, and maintenance of CHP plants. I will conclude with a couple of high-level examples of overall plant layouts. As the name denotes, CHPs produce both heat and electricity, usually from a single fuel source. They can achieve higher efficiencies of 65 to 80%, with some systems nearing 90% efficiency, which is significantly higher than the average 52% efficiency from conventional power generation. And based on EPA statistics, the CHP emits 4,200 tons of CO2 per year, while the separate heat and power systems of a conventional plant emit a total of 8,300 tons of CO2 per year. There are a few types of CHPs to consider for your application. First is a combustion turbine generator with a heat recovery steam generator. The HRSG captures the CTG exhaust and uses that exhaust to heat water. Second is adding a steam turbine generator to the first option. By adding the STG to the process, it can extract energy from the pressurized steam produced in the HRSG to create a second source of power. Third is a boiler with STG option, similar to the first option, except that the boiler is used for the heating process instead of the HRSG. The boiler gets heat energy from the burning process of fuels such as coal or biomass. Fourth option is microturbines. They can be described as a turbine engine with an added generator for electric power in a compact scaled down size. Fifth is fuel cells, and they produce power electrochemically, similar to a battery. Lastly is the reciprocating engine with HRSG option. These are also known as RICE engines, and they are similar to a car engine, but on a very much larger scale. Each option will have auxiliary systems and equipment that may be similar between the types, but there will also be separate equipment specific to each option. Due to time constraints, I cannot cover all of the equipment for all 6 options, but hopefully enough to get started. If you would like more information on any of the 6 options, you can reach out to Dell or myself, or you can write a comment in the chat and we can follow up with you as soon as we can after the webinar. So I'll start with some considerations relating to the site. And typically the client already has a site in mind and have already headed down the path that a CHP is the best option for their specific needs. Some of the factors that will drive major and ancillary equipment needed are proximity to fuel source. Typically, we would see natural gas as the source, but there are other biomass options such as wood pulp or crop residue, for example, in a CHP with boilers as the heat source. Proximity to water. The geographic location of the power plant is a huge impact on cooling technology options and therefore the equipment required. Proximity to energy demand, for example, industrial processes, commercial buildings, or the electrical sector. So from a general arrangement standpoint, the interconnections to those facilities may require trestles, additional roadways, underground duct banks, or overhead power lines. Last is accessibility for general maintenance and operation. Roadways could also be used for the construction of the plant. So this means that there needs to be some consideration for the overall roadway capacity. Factors to consider on any site, whether it's new or existing: the environmental impact, zoning regulations and land use, and geotechnical conditions. In this example, covering environmental and zoning consideration, the proximity to the homes on the left relates to the environmental considerations, those being plant noise and potential hazardous materials like exhaust emissions, fuel gas, and if we're going to use ammonia for SCR, for example. Zoning considerations are to make sure that our site is simply zoned for the proper use. In this case, the purple box with the cartoon building is currently zoned residential, and we would need to rezone that with the county. The third factor is geotechnical conditions, for example, soil stability, flood risk, and water shedding. On this slide, green is considered wetlands by the county. And here I've added the blue and pink to include the flood zones in addition to the wetlands. And so while the client owns everything to the right of the yellow line, only the portions inside the purple boxes are buildable due to the conditions on site. So examples of a well-planned layout include separation of the different areas, easy access, and adequate space for upgrades or expansion. In this first high-level example, it's an existing building that the client was repurposing for a CHP. There's clear separation of the different areas: water storage, water treatment. Electrical was on the second floor above the control room, so it's not shown here. And the hazardous materials are isolated off to the right. And this is only half of the client's building, so future expansion would be to the two bays off to the top of the page that aren't quite shown. Example 2 is a site that I am going to visit again in the fuel handling section of the webinar, but it does highlight those three aspects. Separation of plant area clearly shows access into and out of the plant, as well as the access roads around the power block itself. And it does have space within the property boundary lines for expansion or upgrades. Example 3 is an existing utility whose original building wall ended at column row A. Our addition extended the new plant wall down to column row D. The plant already had most of the services needed to operate a CHP, so the separate areas are limited to the CHP itself. As you can see in this design, we also left space for future additional smaller unit, as well as additional space for future lube oil equipment. Now that we've talked a little bit about the site, I'll cover some of the major pieces of equipment that make up a CHP. Each CHP will have key primary pieces of equipment, and then each key piece will have its own ancillary equipment required to run it. In addition to including the key pieces of equipment in a general arrangement, the various ancillary equipment also needs to be considered in the layout. 3 important things to consider on a GA for gas turbine generator is to ensure there's adequate clearance for maintenance, inspection, and repair. Consider the location of the fuel systems, air intake, and exhaust systems, and allow for easy access to engine controls, instruments, and safety devices. Depending on the size of a combustion turbine, may require any or all of the following ancillary equipment to be part of the general arrangement: fuel pumps, fuel filters, fuel heaters. In regards to air, you need air filters, air compressors, intercoolers. You have the exhaust stacks, exhaust silencers, and you will have starters, batteries, and charging systems. Similar to a combustion turbine, maintenance pole space needs to be included on the GA for both the rotor and the condenser pole space. Ancillary equipment required for a steam turbine will include condenser coils, cooling water pumps, cooling tower, feed water pumps and heaters, a deaerator, and then oil pumps, oil filters, and oil coolers. Reciprocating engines will have the generator mounted on the end of the engine and will require maintenance pole space on that end. They will most likely include the following ancillary equipment: fuel pumps, fuel filters, fuel injectors, air filters. You'll need air compressors for both instrument air and potentially starting air, and you may have turbochargers. There needs to be exhaust manifolds, exhaust silencers, potentially catalytic converters, radiators, cooling fans, water pumps. And in regards to oil, you're going to have oil pumps, filters, coolers, and some kind of storage. Boiler ancillary equipment depends on the fuel, and that could be tanks, additional tanks, pumps, filters, heaters for the fuel, air compressors and filters, gas meters and regulators, water softeners, filters and pumps, burner management system, flame detectors. You may need selective catalytic reduction. If you're burning biofuels, you'll need electrostatic precipitators, soot blowers, water wash systems, boiler cleaning equipment. And then in addition, boilers utilizing biofuels are going to need ash conveyors, ash storage silos, and ash handling systems. The generator is a key piece of electrical equipment. It could be either synchronous or induction type generator. I'm only going to focus on the synchronous type. Synchronous generators are typically what you see in our designs and require an auxiliary DC voltage excitation system. The DC excitation system has two different designs, rotating and static. The rotating designs are built into the generator, require an AC aux power feed, one or two smaller cabinets that are roughly 2 foot by 3 foot, and a small voltage regulator that's typically 1 or 2 small cabinets. The static design requires several large standalone cabinets. Those are roughly 4 feet by 4 feet, and they can be as tall as 8 feet. They also require a large voltage regulator. This list may not be exhaustive, and specific equipment might vary depending on the HRSG design, fuel type, and CHP system requirements. But some of the basic ancillary equipment that may be required are water softeners, filters, pumps, steam traps, steam meters, pressure reducing stations, gas meters, regulators, and filters. This might also have selective catalytic reduction systems, electrostatic precipitators, gas stack analyzers. There could be feed water pumps, circulating pumps, condensate pumps, and air compressors. Next, I'll get into some of the considerations for building design. While a CHP can thrive outside, many clients want their plant to be enclosed. This slide is a short list of some of the basics that need to go into building design. Light wall design and things like man doors, roll-up doors, removable panels for easy access for maintenance and operation. Considerations for building design are how the building is oriented on the site, whether it sits north-south or east-west. If it's possible to place windows or translucent panels for natural lighting, what type of roof design it will have. And one aspect that often doesn't get enough thought at the beginning is whether or not it's stick-built versus pre-engineered. And finally, during the process of the layout within the building, the designers need to consider that the NFPA codes for life safety egress are met. In the previous slide, I mentioned stick-built versus pre-engineered metal building style. These two visuals highlight some of the differences between the two. Pre-engineered metal buildings use engineered columns that taper. The tapers can infringe upon the interior usable area of the building. Aisles, platforms, equipment, and pole space need to be placed far enough away from the base of the building columns so that they don't interfere with the building columns as they taper towards the roof. Often pre-engineered building manufacturers prefer that no other steel is hung from their columns or roof members without understanding all of the loads required. This forces the electrical and piping designers to have preliminary routes for tray, conduit, and pipe to be able to provide those loads to the manufacturer. Many times in a pre-engineered building, additional freestanding trestles need to be designed and added to support piping and electrical as they pass through the plant. Their column grids are placed at the face of the column for the width of the building and at the center of the columns for the length of the building. This needs to be considered when overall building size is determined. The girts on a pre-engineered building are Z-shaped and are placed flush with the outside face of the columns so that only the metal wall panel and slat siding protrude past the face of the column. A pre-engineered building will allow for larger spans without additional support. In a stick-built design, aisles, clear spaces, and equipment can be placed closer to the building columns. Stick-built structures allow for more usable interior space near those exterior columns. Platforms, mezzanines, and catwalks can be framed into the building structure and do not have to be freestanding. Things like equipment, piping, tray, bridge cranes, and stacks can also be supported off the structure. Girt lines are often offset from the outside face of the building column, and this increases the exterior footprint by roughly 1 foot to 1.5 foot. Also mentioned earlier, the NFPA codes for life safety. Those basic codes from Chapter 7, means of egress, and need to be met are safe and quick exiting of the building. Exits must be located in accessible areas. Egress must be properly shielded from fire and smoke, ensuring occupants can safely evacuate. And finally, once occupants have exited the building, that there's a clear path to safety. Each of these two examples are individual pages from an overall life safety plan. Each shows the clearest path and distances to safe exits. To verify all the distances are within code requirements. The example on the left shows the basics of an office space and control room area and its attached electrical room that I'll talk about a little bit later. The example on the right has similar route paths shown, as well as expanded data, including occupancy load areas. So let's look at an overview of electrical systems. We're briefly covering switchgear and distribution, the electrical room itself, and transformers. There are two types of switchgear that I'm going to cover. That's paralleling switchgear and utility grade that can drive the layout. Switchgear controls power distribution and consists of breaker compartments and control compartments that can be either separately installed or integrated into one lineup. Regardless of whether you use integrated or separate layout, there are 4 basic breaker compartments for a parallel with utility application. Those compartments are a utility breaker compartment, generator breaker compartment, a tie breaker compartment, which is optional depending on configuration, and a feeder distribution breaker compartment. In regard to the control compartments, there are 3 basic control compartments and a mimic panel, which is normally just a color touchscreen HMI that will display system 1 line status. Those control compartments are a master system control compartment, and there's 1 required per system. There's a generator control compartment, and there's 1 required per generator, and a utility control compartment, and there's one required per utility source. Utility grade switchgear consists of electrical fuses, disconnect switches, or circuit breakers to control utility transmission. The two control schemes of this switchgear include the Ethernet backbone switchgear and all-in-one switchgear controller. Utility grade switchgear could be either outdoor or indoor rated. Overall sizes of the cabinets can vary slightly based on manufacturer. This is a short list of considerations for the room that houses the switchgear and distribution equipment. Much of the equipment located within the electrical room is large and heavy. Suitable provisions should be made for access into the room and for moving the equipment around. Installation and removal of individual items of equipment should be possible with the electric room live, and care needs to be taken around columns and other obstructions to ensure that clearance distances are maintained. It is good practice and a regulatory requirement to provide at least two means of emergency egress. Doors providing emergency egress should open outward. This is the electrical room that I mentioned in the life safety egress slide. It shows some of the key spacing requirements to be considered. For circuits, this room has been designed for a 13.8 kV system, 8 circuits, and a total of 11 sections. The arrangement is based on 3 480 volt MCCs, 6 low voltage distribution panels, and a 6-section 480 volt switchgear. Minimum NEC clearances always need to be observed. In addition to those clearances, the designer needs to ensure that there's adequate space for operational and maintenance requirements. The layout on the left is shown with the basic equipment only, and it looks fairly open, but when those clearances and maintenance spaces are shown as in the right view, it tightens up the available free space in the room. This layout allows for access to both the front and rear of the equipment. Should the switchgear require only front access, the rear space could be reduced to roughly 4 to 6 inches just to keep it away from the wall. Sufficient height needs to be allowed in the room to ensure adequate movement and operation of the equipment. In practice, a room height of 12 feet is a good rule of thumb to start. Depending on the type of switchgear, this may need to be increased to allow for the exhaust of arc gases during fault conditions. In this case, we utilized an arc chute that exited through the roof. Let's take a brief look at transformers. Here's an example of a 3D model of a transformer, and on the right is a plan view of 2 auxiliary transformers. Transformers will typically sit outside as they're physically very large and oil-filled. Generally, they require blast wall if located near other equipment, and they will typically require oil containment even if environmentally friendly oil is used. This is a plan view of the transformer from the 3D model you saw on the previous slide. You can see that the overall size is fairly large at almost 14 feet by 21 feet. But when you take into consideration my comments from the previous slide in regard to blast wall and containment, we need more space. As you can see, when we add the blast wall and containment foundation, plus any other ancillary equipment, for example, the neutral grounding resistor shown to the left, we end up with space requirements that jump from 14 by 21 feet to an overall space of 24 by 40 feet. Okay, so let's get into the fuel handling and storage. CHP systems operate with a wide range of fuels. Natural gas is the most common primary energy source used in a combined heat and power plant, followed by coal and biomass. If the CHP design utilizes a boiler for heating process, coal or biomass would be most likely the fuel. Most common forms of biomass are wood pulp and crop residue. But biofuel could be anything from ethanol and biodiesel to a pelletized fuel that would typically come from forestry and farming industries. Any of those biofuels will require accommodations for offloading and stockpile locations. They could be stored in tanks, silos, or simply on the ground. These biofuels will also require options for space for the conveying equipment needed to move the material from the storage to the boiler house. Here are 3 different real-world examples to show layout options for unloading and storage of wood pulp. The top 2 are sister plants and have similar layouts and similar storage areas at roughly 125,000 to 135,000 square feet, which is about 45 days of storage. The bottom photo has a much larger storage capacity at 300,000 square feet. All 3 have accommodations for truck scales with a scale admin building. They all have dual truck tippers for offloading. In addition to the storage space, there also needs to be accommodations for the conveyors to move the fuel from the reclaim hopper near the pile to the boiler house. In the top 2 examples, there's approximately 400 feet between the boiler house and the reclaim hopper. The bottom picture, the main conveyor is approximately 600 feet from the hopper to the boiler house. When burning biofuels such as wood pulp or crop residue, there will be ash from the burning process that falls into the bottom of the boiler and needs to be removed. That will add ash handle removal equipment to the interior of the plant, as well as ash removal access and temporary storage to the site itself. Factors that can drive the arrangement for natural gas is whether or not it's already on site. If not already available, it will most likely require a metering station that typically belongs to the gas supplier. When using natural gas, there are other factors to consider for required equipment. The gas yard layout shown in this example highlights 4 of the skids that may be required based on fuel quality. The chemical composition of natural gas can vary depending on the source and geological formation. Natural gas primarily consists of methane, but it may also contain various amounts of other hydrocarbons. The relative proportions of these components can affect the quality and energy content of the gas, known as its heating value. The higher the heating value, the more energy rich the fuel is. Natural gas can have impurities such as sulfur compounds, carbon dioxide, nitrogen, and other trace elements that may need to be removed. The moisture content of natural gas is another factor that influences its quality. Moisture can condense and cause operational issues in pipeline and equipment, so it needs to be controlled within acceptable levels per CHP equipment requirements. Natural gas is transported and distributed under specific pressure and flow conditions. Pressure and flow characteristics include pressure drop and flow rates and can impact the performance and usability of the gas. Excuse me. What you see moving on the left is a 3D model of the layout that was used to create the previous slide. This design takes care of those fuel quality considerations. What we see here is a regulating skid, a water bath heater skid, coalescing filter skid, and a metering skid. In the upper right, we have the real world picture of the finished design in place and operating. And while this runs, I want to mention that you can see underground, we've routed all the underground piping, conduit. This is one of our methods to make sure that we have 0 interferences while we're designing these plants. I like to let it run because it's fun. Okay, final considerations in fuel handling storages in regard to hazardous area classification. This is one of the reasons why the gas yard is typically located away from other equipment. Special care needs to be taken to identify the different designations between Class 1 Div 1 and Class 1 Div 2 hazardous areas. 3 important reasons for the identification and modeling of these areas in the layout of the electrical system to make sure that any electrical equipment within those hazardous areas is rated accordingly. They're identified to make sure that no air intakes to HVAC equipment or into the building are within the identified areas. And finally, when working through the NFPA Life Safety Plan, to make sure that emergency exit paths do not pass through those areas, or that the clear path to safety does not extend into any of those same areas. The example on the left, you can see the light pole was strategically placed so that it didn't have to be classified. The plan view on the right identifies all the various hazardous areas in the natural gas system that we saw from the previous two slides. Now we're going to move into water management. Water management and layout considerations. Position cooling towers to minimize plume drift and to ensure adequate airflow. We want to place boiler feed water tanks near the boiler with consideration for gravity feed and pump suction. When we route condensate return lines, we want to consider how it's routed to minimize pressure drop and to ensure smooth flow. And we want to locate the water treatment area near the boiler or water intake so that there's easy access for maintenance. Layout considerations for wastewater management. We want to position the blowdown tank near the boiler with consideration for gravity flow and drainage. Wastewater treatment systems should be located near the blowdown tank or water intake with easy access for maintenance. We want to place chemical storage and handling in the designated area with secondary containment and spill prevention measures. We want to design drainage and sump systems to collect and manage wastewater with easy access for maintenance and inspection. We want to locate monitoring and sampling stations throughout the plant. Additional general arrangement considerations. Ensure adequate piping, sizing, material selection, and routing to minimize pressure drop and corrosion. Design the drainage and spill prevention layout to prevent water accumulation and spills. Ensure easy access for maintenance and inspection of all equipment and systems. And comply with relevant regulations, codes, and standards for water and wastewater management. This example shows the layout of a chemical building and highlights similar considerations mentioned earlier. Each tank inside the building has its own containment basin, and the acid tank on the exterior has a basin of its own. All three pump skids and the two truck unloading stations have spill prevention curbs. The unloading area also has a dedicated safety shower. There's two doors into and out of the building, as well as a roll-up door for the removal of large equipment. Example 2 is a wastewater treatment area with 2 sets of RO filters, chemical feed tanks, and 3 mixed media filters. The RO skids require a clean-in-place skid, and that's also contained in this room. There's also deionized water storage and condensate storage tanks. As we move into the mezzanine level of example 2 of the water treatment area, we have a few other pieces of equipment. This level shows a catwalk access to the top of the 3 large storage tanks. And there's also a jib crane at the edge to pull replacement mixed media from the ground floor to the mezzanine level for loading into the mixed media filters during regular maintenance. Now let's take a look at emissions and air quality for equipment that could potentially affect the layout. Depending on the CHP type and the equipment used in the heating process, as well as EPA regulations, emissions and air quality equipment will vary depending on what emissions we need to measure and control. CHP plants vary significantly in size, fuel burned, pollution abatement equipment, and geographical location. As a result, monitoring system requirements placed on a given facility will also vary from plant to plant. One key method of control is by using a continuous emissions monitoring system. A SEMS unit samples, measures, collects data, records, and reports the gas emissions information. They can also measure and report gas flow, gas opacity, and moisture content, and will include all of the components necessary for required emission measurements. The SEMS is made up of sampling probes, filter sampling lines, a means to condition the gas being sampled, a gas used for calibration, and a group of gas analyzers geared towards the gas being monitored. They're typically housed in a cabinet that sits at the base of the stack. And the SEMS unit can vary in size depending on the measurements required and the manufacturer. NOx control can be handled through SCR and SNCR equipment utilizing ammonia injection. For SCR, ammonia is injected into the ductwork downstream of the combustion unit, and for SNCR situation, the ammonia is injected into the hot flue gas streams to react with the NOx at high temperatures. Ammonia can also be used with coal by co-firing to reduce CO2 emissions. When burned, ammonia bonds with the oxygen to reduce CO2. It also changes the composition of the flue gas and inhibits the release of hydrogen sulfide from the coal. In an earlier slide, I mentioned ash fallout during combustion in the boiler. There will also be particulate suspended in the exhaust stream that can be removed using precipitators and bag houses. Ammonia solution is considered more efficient than urea and safer than anhydrous ammonia. What we see here is a 3D model of ammonia storage and handling area, highlighting many of the things that we need to consider. The ammonia unloading skid sits on a pad outside the containment area, will require truck access and some form of spill protection at the truck. It's also good practice to install bollards to protect the skid from accidental truck contact. Ammonia is hazardous, so there needs to be a safety shower shown here in yellow. The ammonia tanks are typically horizontal style and elevated to allow access to the valving off the bottom. The elevation also helps with head for pump suction. In this case, the forwarding pump sits just inside the building, shown in green, to protect it from the environment. As we rotate back out of the building, we'll get a better look at the containment. In this case, we had a nearby chemical tank, and we were able to utilize one containment for both tanks. That containment volume must be able to accommodate the volume of the tanks plus 10%, and also allow for extra capacity for rain, snow accumulation in an outdoor situation. As the video ends, I'd like to highlight the last aspect, which is the access requirements, both to the containment area and to the top of the tank. The design and coverage of the platform should consider the safety of personnel working within those areas, ensure necessary maintenance access to all piping and instrumentation. I personally like to work directly with the tank vendors so that they can provide the platform that's going to be attached to their own tank. I work with them on size and shape so that it meets my needs for safe and effective access. And then I work internally with the structural group to provide the stairs and the access required to their platform. We talked a little bit about hazardous area classification in the fuel gas section. NFPA 70 and NFPA 497 defines vapor from aqueous ammonia to be considered a Class 1 Group D hazard. Because of that designation, hazardous areas need to be identified using the same ammonia storage as before. The plan view on the left shows those hazardous areas, and the two model shots show them in 3D space. Similar to the gas yard, these spaces are part of the model and layout and need to be considered for electrical equipment and life safety egress considerations in this area. Particulate control and boiler application is handled with precipitators and/or bag houses. They're typically used when very high efficiencies are required for removing fine particulate matter. ESPs can be installed downstream of the air preheater at temperatures of 270 F to 350 F. They are referred to as cold side ESPs, and they can also be installed upstream of the air preheater where the temperatures are in the range of 600 to 750 F and referred to as hot side ESP. They will require ash removal equipment in the form of collection, storage hoppers, and conveyors. The operating principle of baghouse filters is that the dust-laden exhaust enters the baghouse through the hoppers and is directed into the baghouse compartment. The gas is drawn through the bags and a layer of dust accumulates on the filter media surface until no more air can pass through it. When a sufficient pressure drop occurs, the cleaning process begins. Cleaning can take place while the baghouse is online in filtering mode or offline in isolation mode. The baghouse will require additional equipment specific to ash handling, such as conveyors, blowers, air compressors, and storage bins. So we move into maintenance and access. Easy access allows for quicker maintenance, minimizing downtime, and ensuring continued operation. It also enables safer maintenance, reducing the risk of accidents and injuries. Regular maintenance optimizes equipment performance, leading to improved efficiency and reduced energy loss. Proper maintenance extends the lifespan of the equipment, delaying replacement costs and reducing waste. Regular maintenance can also improve equipment reliability, reducing the likelihood of unexpected failures. Easy access and maintenance help ensure compliance with regulatory requirements and industry standards. Easy access enables quicker identification and resolution of issues, ultimately reducing downtime and losses. Well-maintained equipment allows for flexibility in operation, enabling adjustments to changing energy demands or field resources. While there may be some special circumstances for large maintenance and access clearances, in general, 3-foot minimum around any piece of equipment is a good rule of thumb. Although, as we learned in the electrical section, space requirements are driven by voltage rating of the equipment and NEC requirements. In this example on the right, there's 3 feet of space between each pump. Where space allows, I try to leave enough room off the motor side of the pump that equals to the distance from the end of the motor to the end of the coupler at the pump side, in case one of the motors needs to be pulled and wheeled out of the area. In this case, I had 6.5 feet of clearance. I also try to include a trench near the pump end in a multiple pump installation, or at a minimum, I have a bell up for each pump so that casing drains and miscellaneous inline piping equipment drains don't have to run across the floor. Catwalk widths can vary between OSHA and IBC standards, so depending on the code followed, they should be 22 or 36 inches minimum, and the head clearance of 7 feet for comfortable passage and access to the equipment. Stair widths need to accommodate expected traffic flow and personnel. They need to facilitate rapid evacuation in emergency situations. It's common to see landings every 10 to 12 feet. OSHA requires that 12 feet is not to be exceeded. Landings should be at least 3 feet wide and 5 feet deep. Stairs are always preferred over ladders. Where space limitations require ladder access, ensure that you include a safety cage where required by code. OSHA 29.19.10.27 requires a fixed ladder taller than 20 feet to have a cage, but ASME A14.3 2008 recommends cages for ladders exceeding 15 feet. Local or national regulations may have specific requirements, so it's essential to check the relevant standards and guidelines for your region. Platforms need to be designed to accommodate maintenance tasks with sufficient space for tools and personnel to ensure safe access and egress routes. Lastly, the road access will initially be used for construction of the plant, bringing in construction equipment and supplies, as well as larger components of the CHP, and then ultimately for the operation of the plant. This means that there needs to be consideration for overall roadway capacity on both new and existing roads. For example, to be able to handle a long, low boy trailer with an oversized load, and the radius of the turns, we got to make sure that they're big enough for whatever type of vehicle will be coming on site. To design an efficient and modern control room, there are several considerations that will impact your layout. You must have ancillary equipment, for example, individual USPs for each critical system, an understanding of where the electrical power is coming from, how the building manages ventilation, and how data cables are routed to and from the room. Other factors to consider that will influence your control room layout are the intangible factors, which are often overlooked initially. These things include aspects such as noise control, lighting in the room, and at the operator level, the grouping of people or workstations, as well as the overflow of personnel into and out of the room. And finally, owners and operators often have their own requirements for the control room and admin areas. For example, offices, data closets, and meeting rooms. One of the things that can drive overall size of the room is the type of control monitoring system. Programmable logic controller is local to individual systems, for example, burner management or turbine control. Distributed control system communicates with the local PLC controllers and balance of plant. And the supervisory control and data acquisition is the software that allows operators to see everything that's going on in the plant. There's no one layout that works for every plant. Layout and design is a conversation between plant management and the INC engineers to find out what's preferred. And having that conversation early helps drive the size and layout of the control room. From a layout perspective, DCS typically requires a set of stations to control everything in the plant. PLC-based systems give control local to the equipment or systems in the plant, as well as control within the DCS. Vital systems may need to have their own station in the control room. Fire safety, for example, is a separate station, and it must remain separate from the plant control system. SCADA being the software that shows graphically what's happening in the plant and runs on the DCS. That station could be either in the control room or remotely operated. Other considerations are console design, screen layout, alarm management, networking and connectivity, redundancy, and backup. The placement of operator stations, consoles, displays, and other equipment influence the overall size, layout, and design of the control room. Example one is a 5,800 square feet control room, which is fairly large to accommodate multiple DCS style monitoring systems with 4 operator stations, as well as cabinets for storage of procedures and operating manuals. Also, most control rooms will have hard copies of PIDs and control diagrams. So there's also lay down space to review any of the on-hand documentation. This client had specific needs for training and meeting rooms, as well as offices, a kitchenette, and laboratories. This one is on the 2nd floor, so it required room for an elevator and 2 sets of stairs for egress. Example 2 is 1,200 square feet overall. It's a relatively small control room at 14 by 21. It also has cabinets for storage and lay down space to review any of the on-hand documentation. This specific client only wanted the control room item 24 here, with no additional office space. A single unisex bathroom and shower area, and they specifically asked for kitchenette, item 16 here. We had extra space within the building envelope, so we created a maintenance shop, which is item 22. Regardless of the layout, access control will be required to ensure only necessary personnel have access to the control and monitoring equipment. So let's look at some case studies of successful plant design. This site is in the part of the country where there's a thriving forestry industry. So regards to proximity to fuel sources, it's literally within a 1.5 mile drive for the trucks to move wood pulp from any of the 3 nearby sawmills to the truck tippers on site. Proximity to water, they have 3 wells on site, 2 for production and 1 for potable water. Proximity to energy demand, their power goes directly to a local grid through a switch yard within a mile of the site. And accessibility, the site is within 2 miles of a major highway, and as mentioned, close to the fuel source for the wood pulp. This is the first floor of that same site. Things I want to point out regarding to a bulk of what I've covered in the webinar so far. Starting in the lower left corner is the electrical room. You can see there's ample space for front of and behind the switch gear. As we move to the right, there's a large blank space in the middle. That is the maintenance shop. It has a roll-up door to the exterior for ease of bringing in things like motors and valves. To the lower right on the first floor is the water treatment area, chemical feed, and storage tanks, as well as forwarding pumps. In regards to access, on the left side of the building, there's a roll-up door for an 8-foot wide aisle that traverses through the plant and ends on the right side where there's an access hatch that extends up to the top floor for moving equipment from the ground floor to any of the floors above. Also in the floor is a trench to handle wastewater that extends into multiple areas of the plant, including under the steam turbine, maintenance shop, the water treatment area, and to the blowdown tank at the top of the page. Along that wall at the top of the page is ash conveyor that carries ash from the boiler along that wall to the ash silo in the upper right corner. This is the second floor of the same site. Typically above the electrical room is where we like to place the control room. This control room also includes an I&C shop and a shift supervisor's office. Above the maintenance shop and water treatment area is the bathrooms, lockers, break room, and a couple of offices. To the left is the steam turbine. The lower side has room for rotor pull, and the upper side, where the condenser is, has room for the condenser pull space. Just below the boiler, I want to point out 2 heat exchangers and the length of the pull space required for cleaning and maintenance that often gets overlooked. Out to the right is the precipitator. There's an ID fan between the building and the precipitator, a control room under the inlet duct to the precipitator, and access platforms for both testing and access to the top of the precipitator. Off the upper side of the precipitator, you can see the conveyor that carries the ash away from the precipitator back to the plant and into the same ash shed that the boiler uses. The elevation of this boiler with CTG plant has a couple of things to point out. Above the steam turbine generator is a 20-ton bridge crane with a 5-ton auxiliary hoist for the rotor and condenser pull. The elevation of the wood bin that feeds the screw conveyor for the boiler is partially what sets the distance between the reclaim hopper and the power plant itself. There are accommodations in the roof for ventilation. As mentioned before, you can see the access platforms on the precipitator for the inlet duct and outlet duct access, as well as performance sampling in the vertical section of duct. Case study number 2, this site is tucked into the only buildable corner on the client's property. And it covers those same 4 aspects: proximity to fuel sources, proximity to a water supply. The client, let me go back to the fuel. They do have fuel on site, but it's not near the location for the new CHPs or at the correct pressure. So we had to bring gas in from a different location. We compress it in the gas yard, which is item 4 in the upper left corner, where we have gas compressors, aftercoolers, and a knockout drum. In regards to the water supply, the client has plenty of water on hand, but only in the existing buildings. So we needed a trestle, which is item 6, to bring the water and other utilities from the existing plant to the new CHPs. We will use the same trestle to take both power and steam back to the existing plant. Proximity to energy demand is obvious. The client has a large manufacturing facility that can use both the steam and power produced. And accessibility, because the plant arrangement is contained within the existing site, the client already has access road onto and out of the plant. One of the biggest challenges with this site was that our 2 CHP plants needed to be wedged in between an existing storage tank, existing roads, and an existing railway. The only item that could be relocated was the roadway, but only by a limited distance. This is a plan view of one of the powerhouses in that case study too. This plan view pulls together some of the equipment I talked about in the equipment section. The combustion turbine has an air inlet filter off to the left and access under the filter for the generator removal. There's a space toward the bottom of the page for engine pull space. That is here. We pulled cooling air for the enclosures from the outside wall. That duct work is shown in items 126 and 127. We have a bypass stack between the CTG and the HRSG. And I think we go to conclusion. So a well thought out general arrangement for a combined heat and power plant provides numerous benefits, including efficient use of available space, reducing footprint and costs, ease of access and maintainability to equipment, clear escape routes, reducing tripping hazards and safe access to equipment, optimizes equipment layout, reducing heat losses and improved overall thermal efficiency. Intuitive layout reduces operator error and improving overall site system control. Scalability and flexibility allows for future upgrades or modifications with minimal disruptions. Optimized ventilation and air intake, reducing airborne contaminants. And the well-planned layout, enabling faster construction, installation, and commissioning. This is where I turn it back over to Dale.
Thank you, Kent, for sharing your knowledge and your expertise in this area. Really appreciate it. It is now time for our Q&A session. So if you have a question, please feel free to put it in the question and answer chat box on the GoToWebinar tool. I do know that it's past time. It's about 1:03. So if you do need to go, you can head on out, and you will be getting a link to the recording of this video. So if you'd like to watch that later or check the Q&A at a later date, you can definitely do that. You can share the link with people that you know, all that good stuff. So while we wait for a moment, can you go to the next screen there, Kent, the next slide? All right, so again, thank you for coming. Still waiting on some of the Q&A stuff to get sorted out. Remember to look out to your email for those 2 documents to confirm your PDH. And then also October 23rd, around that date, we're looking at our next Commonwealth webinar on the topic of 3D modeling. So with all that said, We are at 1:04 and didn't get any questions in this time, which is great. Kent, you did a really good job explaining it all. So I think you may have answered any pressing questions. If something does come up, if somebody, or if you are interested in something Kent mentioned or would like some more information about anything on this topic, you can reach out to myself or the Commonwealth marketing team. Our email has been in the communication from GoToWebinar, and we'd be more than happy to get you connected with the folks who can get you the right answers quickly, promptly, and with a friendly smile, obviously. So thank you everybody for joining us today. We're gonna sign off here in a moment. Again, thank you, Kent, for your time, and everyone, have a wonderful Thursday. Talk to you later.